Okay, yes, I'm going to talk about young and ill-behaved stars. They're kind of like young people. They have a lot of whims and crazy things that they do. So pre-main sequence stars are what I'm going to show you, and I'm aware that this is the last talk before dinner, so maybe you're all tired or hungry or both. So I'll try not to saturate you with too much information, but what I want to do is show you some really exquisite space-based light curves, maybe some of the sort that you have not seen before. So before I do that, I need to thank a number of collaborators. Our project is essentially headquartered at Caltech. We have a small group there. We also have dozens of international collaborators who are too numerous to list here, but you're welcome to visit our website and find out more about who's involved and what we do. So, young stars at ages of a few million years are what I'm focusing on. These are, I'm going to talk mainly about the low mass ones, so FGKM stars. Many of these at these ages are surrounded by dusty disks from which they are accreting gas, we think, along magnetic field lines, as shown here. Now, these systems emit at a wide variety of wavelengths. The inner disk is separated from the stellar surface by around 1/10 of an AU, and you get mid-infrared and near-infrared radiation from that region. The central star itself emits in the optical, and then you also get UV and X-ray from the accretion shocks where the gas material hits the poles of the star. At least that's what we think that happens, but this is actually a rather simplified picture, and we have reason to believe that reality is much more complex. So this is a static axisymmetric picture here, and what we want to know is how young stars and their disks actually differ from this simplified picture. So what's missing? What do we want to know? I'll focus on three main areas. We'd like to know about inner disk structure around these pre-main sequence stars, and recent imaging of full disks, so at size scales of several hundred AU, have revealed interesting spiral structure, some of which you can see here. We'd like to know if those kind of structures persist in the inner disk region. We're also interested in the dust properties of the inner disk, and in particular the grain size and grain growth, as this may affect terrestrial planet formation. And finally, as some people have alluded to today, the star-disk interaction is very important, and perhaps the magnetic fields are not dipolar, as I just showed you, but maybe more complex, and that affects how the material funnels onto the central star, and as well as the angular momentum exchange. So why are these issues so difficult to study? The problem is the size scale. So for the nearest star-forming regions, you simply cannot resolve the inner AU, which is where all of these things are going on, not even with the state-of-the-art interferometers like ALMA. You can't directly image it. We need something else. And so what I hope to convince you is that that something else is variability, which we can use to essentially tomographically map the structure and dynamics of from the stellar surface to the inner disk rim as everything rotates and orbits around in these systems on time scales of a few days to a week. So how do we actually do this? We acquire light curves, hopefully very high quality light curves, so that we can morphologically classify what's going on in those light curves. We search for correlations with the known star and disk parameters, and then we compare with models for mechanisms of the variability that we're seeing and try to understand what's going on. So these activities would really not be possible, or they would be very difficult were it not for the revolution that we've had in time series monitoring of young stars from space. We have the MOST telescope, CoRoT, and Kepler, which actually has not observed pre-main sequence stars yet, but we hope that K2 will. And to help you appreciate just how amazing the space-based light curves are, here you can see some ground-based light curves in the optical on timescales of just a few days, and the fluctuations that you're seeing in those light curves are, a few tenths of the magnitude. Basically, you can see that they're variable, but because of the precision and the time sampling, you can't say much more than that from the ground. But we brought in space-based photometry And here are some examples thanks to CoRoT. Suddenly, you can start to make out features in the light curve in detail. These are light curves on showing 2-week timescales of variability with amplitudes of up to 50% here. These are young stars in the NGC 2264 cluster. Now, at the same time as this optical revolution in time series photometry, I'd also like to highlight what's been going on in parallel in the infrared thanks to the Spitzer Space Telescope. And around the same time as all these optical space telescopes have been operating, we've been getting data at 3.6 and 4.5 microns in the infrared from Spitzer. Prior to its launch, we did not really have a good idea of what sorts of variability we would see around these young stars. The emission at infrared wavelengths, as you may recall, comes from the inner disk region, and people thought that the inner disk would just be sitting there, not really varying, and why should we even look for infrared variability? So we had the idea to train the Spitzer Space Telescope on young star disk systems and just see what was there. And lo and behold, a few years ago, we detected strong variability in some young cluster members shown here. These are 2 weeks of data, and you can see that the inner disks of these objects are varying at the 10, 20, even 50% level. So turns out these stars are not only variable in the optical, but they are also highly variable in the infrared. Why not combine the two wavelengths and see if we can learn even more? So thus was born the idea of the Coordinated Synoptic Investigation of NGC 2264, quite a mouthful, so we call it CSI 2264 for short. And in short, we used CoRoT and Spitzer in tandem to observe young cluster members at a few million years of age for over a month straight continuously. And not only that, but once we got this idea, we thought, why use 2 space telescopes when you can use 3 or 4? So we also brought in the MOST telescope, the suitcase, and the Chandra telescope, observing for a brief time in X-ray at the beginning of this whole campaign. And then we also recruited over a dozen ground-based telescopes to get other data from other bands as well as spectroscopy. So this is really a massive project, and it's described in a recent paper of mine that came out in the Astronomical Journal a few months ago, if you'd like more details. So we, as I mentioned, we use these telescopes to look at the NGC 2264 cluster, which is very well studied. It is somewhat far away, but unfortunately it was the only cluster in the field of view of CoRoT, so that was the reason for its choice. It's a few million years old, and within a square degree there were several thousand young stars that can be monitored all at once with both CoRoT and Spitzer, many of which have disks. So, are you ready to see some light curves? And I should mention for those that are taking pictures with your cameras, there are many more light curves in the paper that I just mentioned, so you can see all of them in here. So we looked, we basically mapped out the region at 2-hour cadence with Spitzer, looking at about a 0.8 degree field of view. And sure enough, over the 30 days of observation at 3.6 and 4.5 microns, we saw incredible variability. The amplitude scales on here are shown in 0.1 magnitude intervals. It's cut off, but the arrows all mark 0.1 magnitudes, and all the durations are 30 days. So as you can see, there's quite a variety of variability. Not really periodic, although some of it is, and there's a variety of timescales involved. With CoRoT, we looked at a square degree region of this young cluster, at some young cluster members, and then also some field stars to fill out the data collection. And again, the data were very high quality. It's all about 1% precision or better. This is 40 days worth of data. This is just a small sampling of the types of light curves that we see in the optical. And again, you could see the arrows marking the 0.1 magnitude range. This is really amazing light curves. So what happens when we combine the optical and infrared? We initially wanted to know the relationship between optical and infrared variability. Turns out it's more complicated than we thought. So we have essentially a veritable zoo of light curves, and here we combine the CoRoT data in black and the Spitzer data in blue and red, and then also the vertical bars mark times when we had high-resolution spectroscopy to look at things like H-alpha emission and lithium lines. So these are examples of some of our ill-behaved young stars, which are doing wild and stochastic things, which may be related to accretion, but also to their circumstellar disk material, which is swirling around them. So these ones are not periodic. Some of them are periodic, but not perfectly so. And sometimes you can see that the infrared is about the same amplitude and very well correlated with the optical. On the bottom is just infrared behavior. These are two examples of what we would call quasi-periodic light curves. You see changes from one cycle to the next, and it's not clear what the variability mechanism actually is. It seems too ill-behaved to be star spots. In other cases, there are quasi-periodic fading events, which you can see here prominently in the optical with CoRoT, but you also tend to see them not so prominently in the infrared, so there's partial correlation between the two light curves. What we think in these cases is that there are blobs or warps in the surrounding disk, which are periodically occulting the central star, although there's probably some rearrangement of that material each time it goes around, hence the different depths of the dips. And so in some cases, the optical and infrared correlates very well, and we can kind of match them up and see how the amplitudes compare. And so in this case, I've changed the color scheme, sorry, but Spitzer is now red and CoRoT is now blue, and I've scaled the Spitzer light curve up by a factor of 4, so you can see how well it matches. Now, if you assume that this variability is due to material which is occulting the central star, kind of like a dusty screen, then you can look into the extinction law that is implied by the variability amplitudes, and it turns out that it would be very non-interstellar. If it were interstellar dust, you would expect the infrared amplitude to be a factor of 20 below the optical, not a factor of 4. So that tells us something about how the dust in the inner disk has evolved. One of the highlights of our CoRoT data set was the discovery of these brightening events, which occur frequently in some of the light curves. And you can see an example here where the light curve basically has all these brightening events, which are a little bit too long to be stellar flares and also a bit too symmetric. And what we think those are accretion bursts, where the material is not flowing steadily onto the star, but you're actually seeing discrete events where the material crashes onto the star and you get a brightening. This is, we have another entire paper on these types of light curves, and this is supported by the fact that these objects tend to show preferentially high UV excesses. So they are the most strongly accreting objects in the data set. Here are a few more examples of these types of objects, and you can pick out on quite short time scales, thanks to the amazing cadence and precision of the data. For the first time, you can really see all these events going on that were impossible to make out from the ground. Now, in other cases, there's some bizarre infrared behavior where there isn't much at all going on in the optical in black, but there are large amplitude excursions in the infrared, sometimes on fairly short time scales, like even a few days. And I think it's safe to say we have no idea what's causing that variability, but there's really nothing going on at the stellar surface, so there has to be some sort of process in the inner disk that's perhaps causing the inner rim to go up and down and shadowing the disk, thereby changing the flux and causing these variations. We have a number of light curves that look just like this, so it's very interesting, and we're actively working to try to figure out what's going on. So I just showed you an examples of the wide variety of light curves that we have in this cluster. And to sort of bring it back to the schematic I showed you in the beginning, We have gotten some really amazing light curves, and we have now performed a full morphological classification of all the different types of behavior we see and their incidences in both the optical and the infrared. And so now we're looking for correlations with the other properties of these stars and disks and hoping to get some modelers interested in explaining what we're seeing. So basically we've gone from this to this, and there are something like 8 different types of variability that we've been able to pick out thanks to the high quality of these light curves. And finally, what have we learned? So we are learning about inner disk structure from some of those, the dip-like light curves that I showed you. There's almost certainly asymmetries in the disk that are occulting the star when they're aligned in the right way. We see some interesting changes on fairly short time scales that are maybe even too short to be explained by disk dynamics. We're also, we think, seeing unsteady accretion, so that's giving us clues about how the star and the disk are interacting and how the material is actually flowing on in an unsteady manner. And finally, those obscuration events that I showed you are enabling us to get at the properties of some of the dust in the inner disk. And so I will leave you with this picture that shows us that these young accreting stars are perhaps a lot more crazy than we even thought they were before. Thank you.
Any questions for Anne-Marie? Well, I'll start off with one question. For these objects which show, not really much going on in the optical and some variability in the Spitzer band that's really uncorrelated with the optical, have you considered the possibility of blending? Because both satellites have a fairly big PSF.
Yes. So initially when I saw these light curves where there was nothing going on in the optical and wild excursions in infrared, I thought, oops, I messed up. But first of all, there are a lot of them. And second of all, we actually specifically examined the raw images of a lot of these objects, and typically we have had a few problems with blends, and we often see a star nearby in the PSF, but they'd have to be totally unresolved for this to be the case. So it's a possibility that all of these are, binary systems, but it just seems unlikely given the number of them.
And otherwise, would variable dust emission be a possibility? So where you're not seeing occultations by dust, but you are seeing variations in emission from dust?
Yes, so I think the crazy infrared behavior is not occultation, since we don't see anything going on in the optical. You should see that. So something is literally causing the disk emission to change on fairly short time scales. Yep.
Okay.
So do you have any, for some star in your sample, do you have any independent information on the magnetic field structure of the stars, for example, using spectral polarimetry?
Yeah, so unfortunately, the NGC 2264 cluster is a bit too far away. The stars are not particularly bright. So I'm hoping in the future with K2, for example, we'll be looking at closer stars that are closer by and easier to study with those sort of methods.
Any more questions? Oh, one more.
Anybody try to make real models of all this stuff rather than sort of hand waving, disk doing this and disk doing that, and physically based models of what's going on?
Yes, well, it's been a little difficult to attract modelers, I guess because what we're seeing is so complicated. Yes, there are a few models out there, specifically models of magnetospheric accretion by Romanova and collaborators, and they have in fact predicted different regimes of accretion depending on the accretion rate itself. And they predict at lower accretion rates, you have stable hotspots on the star, and higher accretion rates that you see, unsteady accretion and sort of more blobs. And that does seem to be consistent with our observations. So that's at least one model that we're maybe confirming. But yes, we're happy for people to make more models of our data.
One last question from Tim.
Yeah, hi. Have you done any Fourier analysis to look for high frequency oscillations, maybe oscillations in the disk or something like that?
Yes, so we have done Fourier analysis on most of our targets. And what I did not show were the non-accreting stars. In fact, as you might have noticed, I didn't mention spots at all. We have a lot of that in our data set. I was just showing the more wacky ones. So we've done Fourier analysis on those, and then the ones with disks, we don't see anything particular at high frequency. We mostly just see basically like a 1/f noise trend consistent with accretion.